Now, it turns out not any kind of supernova will provide this standard candle for us. There's a special class of supernovae called type 1a supernovae. This was first really explained by the famous Indian astrophysicist Chandrasekhar in the 1930s, that a star, actually the core of a star like our sun, called a white dwarf star in a particular configuration, can only hold back the crush of gravity up to a certain critical mass, known as the Chandrasekhar mass. So that's all well and good. That white dwarf star can be happily holding up the crushing force of gravity by a special kind of, it's called electron degeneracy pressure. But if another star, let's say a companion star, starts spilling material over onto that star, little by little, the original star, the white dwarf, can grow in mass until it crosses Chandrasekhar's limit, and then you will get a runaway thermonuclear explosion. You have the inability to hold back gravity, so the star crushes and fusion occurs throughout the star immediately. This is a great formula for a standard bomb, right? You have, in this case, 1.4 times the mass of the sun. Runaway thermonuclear explosion leads to a very uniform luminosity, about 4 billion times the luminosity of the sun at peak. What's also so great about these objects is we can see them very far away. You want a standard candle that's very luminous, so we can see these halfway across the visible universe, maybe 3/4 of the way with the Hubble Space Telescope. So in my graduate work, I started looking for and measuring these supernovae. Here are 4 of the ones that I studied in my thesis from 1995. You might wonder, how do we find these supernovae? And well, you can see it's quite easy. You just look for the arrows in the pictures, and there's usually a dot at the end of the arrow. No, we add the arrows in Photoshop later. No, but how do you really find a supernova? Well, it's a needle in a haystack problem, or it's trying to win the lottery. It's incredibly rare, so there'll only be one, as I said, in a galaxy like ours about every 100 years. So the way you win the lottery is you buy all the lottery tickets, right? So in our case, what that means is we recognize that we can turn the odds in our favor if we have enough lottery tickets. So if there's one in a galaxy like ours every 100 years, that means there is one supernova in 100 galaxies in a year. So you monitor 100 galaxies, you'll probably find a supernova in a year, but we want many more than that, so then you start monitoring thousands or tens of thousands of galaxies at the same time. You saw that picture I showed you in the beginning. We can easily take images that have tens or hundreds of thousands of galaxies all in them, and then you use computers. Computers are very good at doing this very monotonous process of taking 2 sets of images separated by some period of time, typically a month or a week, and digitally matching them and subtracting them and alerting a human observer that there's a new point of light that has appeared between the 2 exposures, and this often turns out to be a type 1a supernova. I could say more about that later if people are interested. Okay, so in the mid-1990s, my colleagues and I had been good at measuring nearby supernovae to measure how fast the universe was expanding, so we began using large telescopes to measure the very distant supernovae that would tell us about the past expansion rate that we could compare to today. And so we formed a team, and just to show you how strongly convinced we were measuring the deceleration of the universe. You have to come up with a credo or a tagline, and so ours was to measure the cosmic deceleration of the universe with type 1a supernovae. Except we got a great surprise when we did this, and I was the sort of tip of the spear for seeing this surprise. By about 1997, we had collected our first significant set of these supernovae, and it was time to see what the answer was. And so just to remind you again, I was using the supernovae to measure the deceleration of the universe that would equate to some amount of mass in the universe that would tell us whether we had escape velocity. And so I was using a very simple equation that the deceleration would equate to the mass of the universe, and I wrote a little computer program to tell me, okay, fit the data and tell me what the mass is of the universe. I wanted to jump right to the answer. Don't even tell me the deceleration, just let's go right to the right-hand side of that equation. And this is the key page from my lab notebook. So the mass should have been either a small number, like 0.3, or a big number like 1. And instead, it was a negative number. Now, this made no sense. There's no such thing as negative mass. But computers don't know physics. They just know, what you tell them and what they can fit. So when I gave such a simple equation and forced the computer to find a match to the data, it wasn't able to say, hey, dummy, you should notice that the universe is not decelerating, that I need to change the sign on the left here, but you're not letting me do that. You're only letting me play with mass, so I'm going to change that sign. So I realized pretty quickly that that is not physical, that you need something else, something like Einstein's cosmological constant. So I've added here now another term that, as you see, can act the opposite way. You could explain the universe accelerating only if you have something very much like Einstein's cosmological constant, not just have it, but it actually has to be dominant. It has to be more important, larger in size than the mass in the universe. We equate mass and energy frequently in physics, so you understand that I'm saying that the energy of this has to be greater than the energy of that. So a few days later, I started thinking about the cosmological constant. Could this be what was going on? And here's another page from my lab notebook where I was calculating the likelihood that this really was in the data, and it was quite high. It was high enough that I had to admit that it was time to talk to other people about this, that this was probably not just what we would say a fluke or bad luck. I did a lot of cross-checking to make sure I hadn't made a simple mistake, and then I contacted my colleagues. I was collaborating with about 17 astronomers spread all over the planet. We spread all over the planet because, well, it's always nighttime somewhere on the planet, and we're observing these supernovae all the time, so it's very useful to have colleagues in South America, Hawaii, Europe, Australia. And so over the course of about 24 hours, we began a discussion of, do we really believe these results? And I'm going to show you some emails back and forth from that discussion, because it's very interesting to see how scientists react to something unexpected. Scientists tend to be very conservative because most new things turn out to be wrong. My colleague in Berkeley, California, Alex Filipenko, wrote to the team, Adam showed me fantastic plots before he left for his wedding. Our data imply a non-zero cosmological constant. Who knows? This might be the right answer. Bruno Leibengut from Germany, who is a supernova expert, responded, concerning a cosmological constant, I'd like to ask Adam or anybody else in the group if they feel prepared enough to defend the answer. There's no point in writing an article if we are not very sure we are getting the right answer. Brian Schmidt, my colleague who had helped find the supernovae, wrote from Australia, I agree our data imply a cosmological constant, but how confident are we in this result? I find it very perplexing. My thesis advisor, Bob Kirshner, at Harvard, but on sabbatical in Santa Barbara, wrote, I am worried. In your heart, you know the cosmological constant is wrong. Though your head tells you that you don't care and you're just reporting the observations, it would be silly to say we must have a non-zero cosmological constant only to retract it next year. Mark Phillips in Chile, my colleague there, as serious and responsible scientists, we all know that it is far too early to be reaching firm conclusions about the value of the cosmological constant. John Tonry in Hawaii, who remembers the detection of the magnetic monopole and other gaffes. On the other hand, we should not be shy about getting our results out. He's referring to, there are many famous misdiscoveries in physics, and we didn't want to be the next people to discover cold fusion or magnetic monopoles or any one of these things. But it's funny in physics, sometimes you have to play the hand that you're dealt, and this is the hand that we had. Alex Filipenko, if we are wrong in the end, then so be it. At least we ran in the race. There was another team located, I was at the time working at UC Berkeley down on campus, and there was a competing team at the Lawrence Berkeley National Lab, which was a Department of Energy lab, doing the same experiment. So there was a feeling of competition and an interest in working well but quickly. So then I responded, the results are very surprising, shocking even. I've avoided telling anyone about them because I wanted to do some cross-checks. I have, and I wanted to get further into writing the results up. The data require a non-zero cosmological constant. Approach these results not with your heart or head, but with your eyes. We are observers after all. Alejandro Clocciati from Chile wrote, if Einstein made a mistake with the cosmological constant, why couldn't we? I never quite understood if that was supposed to be reassuring or not. But you know, I guess if the grand old man had made this mistake, well, we'd be safe too. Nick Sunsef from Chile. I really encourage you, Adam, to work your butt off on this. We need to be careful. If you are really sure that the cosmological constant is not zero, my God, get it out. I mean this seriously. You probably never will have another scientific result that is more exciting come your way in your lifetime. Of course, Nick was right. So in 1998, we published this paper, Observational Evidence from Supernovae for an Accelerating Universe and a Cosmological Constant. In other words, it looked like the universe was about 70%, you'll keep hearing this number, 70% in the form of dark energy, something like Einstein's cosmological constant. And the other competing team came to the same conclusion about the same time. So this rapidly became part of the story. In fact, it became the breakthrough of the year for Science magazine in 1998. Apparently, Einstein himself would have been pretty amazed that this feature, what some people might have thought was a bug, but really a feature in general relativity, was actually being exercised or actually being witnessed in the universe. So why do we actually think the universe is accelerating now? Well, in detail, we really don't know. That is, we have a kind of general story, hand-wavy, word salad, but we don't really understand the physics or the nature of this dark energy. So sometimes we refer to it as the vacuum energy. So there's an idea that comes to us, well, a feature of quantum mechanics, quantum theory, the physics of very small objects, that the vacuum is a very rich place where particles appear and disappear, that we cannot have total certainty that it's empty. As a result of that, we actually have certainty that it is a very active place with lots of energy of this type. But when we try to calculate all the energy states that are possible, we get an answer that's about 120 orders of magnitude off from what would allow our universe to exist. So, as I said, that's an idea, and it smells like what we're seeing, but there's a giant disconnect between calculation and actual observation. Maybe we could ask Brian more about that at the end. Nevertheless, this is still a very powerful idea. We have seen other, I would say, dark energy in the universe. If you've heard about the Higgs field and the Higgs boson, this is a built-in energy and a built-in particle in space that would act like dark energy. It's not the dark energy or all our dark energy, but it is a place where we've been able to touch and see that empty space has actual activity in it, has actual important physics that we just don't understand that well. It could be we have a dynamical dark energy. So this would be like a time variable or changing form of this. It would be a vacuum energy that changes from place to place and time to time. It's associated with a field. You could think of the electric field or the magnetic field. It has a value in all places, but it will change with time. This sounds like a weird idea, but we actually believed that something like this, an episode we call inflation, occurred shortly after the Big Bang, when the Earth was actually dominated by a temporary vacuum energy that caused the universe to accelerate greatly, tremendously, exponentially, much greater than what we see now. That period ended. Perhaps we are entering a new sort of gentler version of that. Or it still could be that we don't understand gravity, that we still have the wrong theory of physics, and dark energy and dark matter and these extra parts are just the the ether and the epicycles and the extra stuff when you don't have the right theory of physics. But I would say these in order are probably our best guesses. Now, back in 2000, this was such a crazy set of possibilities, we worried about something just much more basic. What if we were just wrong? What if when we saw a distant supernova and thought that distant meant faint, like the ship captain, that a faint lighthouse meant far away, what if we were being fooled by something, in which case the universe wouldn't be accelerating at all? How could we be fooled? Well, there could be a kind of, I talked about fog, a kind of cosmic fog, what we would call dust, gray dust. If it lived in between galaxies, it would make distant objects look faint. Now, nobody had ever seen this gray fog before, but then nobody had ever seen dark energy before. So you couldn't use Occam's razor and say one is crazier than the other. We actually had to go out and prove it. Another possibility could have been that there was an evolution, that we were looking at supernovae that were born when the universe was much younger and actually had less chemical enrichment. Maybe those supernovae were born fainter. So the idea here is when we looked out at something faint, that meant that it was far away and hence there was dark energy. But what if instead faint meant dusty, not so far away, and there was no dark energy? So we realized that if we could look out even further to more distant supernovae, this story, where we're looking through some kind of fog, would just continue to add up. We would keep seeing things look ever fainter. Or if there was this evolution, younger supernovae in the universe were fainter, that would continue as well. Whereas if we really had this new cosmological model where there's dark matter and there's dark energy, the universe would have decelerated in the beginning, and it only would have accelerated more recently. And we should be able to witness this change that would break the degeneracy, I would say, with these other stories. Now, in order to do that, we needed to use a more powerful telescope, more powerful than what we had mostly used before. Here's a short history of the improving power of telescopes. This is compared to, let's say, here's Galileo's telescope. Got about almost a factor of 100 improvement in sensitivity over your eye. And then telescopes got bigger. We moved them to better sights. We changed the detectors from our eyes, which are not very efficient detectors, can't integrate light for very long, to photographic plates, and then to electronic detectors. And then sometimes we're really lucky when astronauts go and put a telescope up into space, the Hubble Space Telescope. It sits above the blurring effects of the atmosphere. If you've ever sat in the bottom of a pool and looked up at your friend outside the pool, everything looks all swimmy and wavy. Well, that's what happens to the lights that we see from stars. So when we put that telescope above the atmosphere, we can get very sharp images. So here is the image of a supernova and its host galaxy as seen from the ground, same one as seen with the Hubble Space Telescope. And if your goal is to be able to measure the brightness of the supernova without the light from the host galaxy, you can see that's an easier job here on the right. And then we've been particularly lucky. The astronauts sometimes return to the telescope and put state-of-the-art technology, newer detectors in there, and that improves our ability to observe the very distant objects. So in early 2002, the astronauts put the advanced camera in, and we used it to find about 25 of these type 1a supernovae, all from this earlier era of the universe, when it was still decelerating, when it was still compact before it gave way to dark energy. And we were able to rule out those alternative stories as well as the original cosmological models to get a convincing case that we live in a universe that has both dark matter and dark energy, that was decelerating in the beginning when everything was very compact, but as it got larger, at some point there was a transition, we believe about 5 or 6 billion years ago, and the universe is now expanding about 20% faster due to this dark energy. Now, it's not just dark energy, it is not just acceleration as witnessed by supernovae that convince us that the universe is filled with dark energy. We, as you saw in the email, scientists are very conservative, and we like a lot of redundancy and cross-checking. And so now there's about 5 or 6 independent lines of investigation which give us this same picture. Supernovae were the first in 1998. In 2003, we saw evidence of what's called the integrated Sachs-Wolf effect. So that means that there are photons of light from the cosmic microwave background which are on their way to us, but along the way they run into these kind of potholes that are the gravitational potentials of clusters of galaxies. And they kind of fall into this pothole, they gain energy that way, and they kind of climb back out, they lose energy. But dark energy acts to pry apart or overcome the gravitational attraction in the cluster, and so the amount of energy that they lose when they climb out is less than when they fell in. That allows us to measure the universe as 70% in dark energy, same answer that we got over here. Another way we can tell is we look at the global geometry of space. There's a relationship between the geometry you see in space and the amount of mass or energy in that space. This has been measured exquisitely with observations from the cosmic microwave background that tell us that the total energy or mass in the universe is in our kind of funny units, 1, whereas when we actually measure how much just mass there is, including the dark stuff, that's only about 30%. So this extra piece, 70%, is obviously there. That's, as I said, independent line of investigation that tells us this. We've seen the action directly of dark energy. The largest clusters of galaxies are always pulling in new members, new galaxies, because they have a lot of attractive gravity. But on the largest scales, they've become less effective at doing that. We have seen the arrested development of the largest cluster of galaxies that allows us to measure the amount of dark energy, again, about 70%. And something else I've been working on recently is to bookend the universe, to take the initial conditions of the universe as measured from the cosmic microwave background and use them to predict how fast the universe is expanding today. And by comparing those two, we again get that the universe is about 70% dark energy.